Okay, and so the third and final of the long talks in today's first session is going to be given by Jiahui from ETH Zurich. Jiahui received his bachelor's and master's degrees from Polytechnic University of Turin and the Technical University of Munich in 2019 and 2021, respectively. He's currently pursuing a doctoral degree at ETH Zurich. His research interests include high-level synthesis and hardware formal verification. Please.
Okay, thanks a lot for the introduction. Today I'm going to give a presentation. The work is given by ETH Zurich and UPC Barcelona, entitled Eliminating Excessive Dynamism of Dataflow Circuits Using Model Checking. Dynamic HLS is a promising alternative to static HLS for designs with irregular workloads or memory accesses. For this type of application, static HLS creates pessimistic schedules during compilation time, whereas dynamic HLS creates dynamically scheduled circuits that are able to adapt their behavior on the fly. And one particular flavor of dynamic HLS is to generate data flow circuits. This paradigm is able to extract maximal parallelism from your applications, but however, the fine-grained handshake logic also adds significant amount of resource overhead. I would like to further address this problem by doing a qualitative construct between dynamic HLS and static HLS. If you decide to use dynamic HLS to speed up your irregular workload that has unpredictable control flow or irregular memory accesses, well, you pay a lot, but you also gain a lot of performance benefits. However, if you still decide to use dynamic HLS to accelerate your regular workload, in this case, you pay the high cost regardless, but with no real performance benefits. So why is that the case? We can look into the product that is generated from dynamic HLS. So this is a circuit that is generated from the code snippets on the left-hand side. And we can directly, briefly introduce you the building blocks of it. So we have merges and branches. They're used to steer tokens based on control flow. We have forks. They're used to duplicate data tokens for parallelism. We have buffers and FIFOs that are used to hold data tokens. And furthermore, in between data flow components, we have data flow channels that pass tokens around. And each data flow channel is a bundle of data values or ready signals. So despite now you can see that they implement conceptually simple functionalities. But however, if you open up the boxes and you look at the logic behind it, you'll see that this is actually very expensive. So in this presentation, I would like to address the question, is expensive data flow logic always needed? And if it is not the case, how can we take advantage of it? How can we spot the redundancies? How can we remove the redundancy? And how can we make sure that everything is correct? Let's start to get some intuition by simulating our circuit. So we trigger the execution of the circuit by injecting a iterator token into a loop. In each iteration, the iterator token is used to trigger load operation, store operation, and also a new iteration. Since we have a difference in terms of propagation time in different passes, the address reaches the store operation early. As a result, the FIFO has to hold the address token until the data token arrives. So let's resume the simulation and let's wait until the data token arrives. So we simulate for 1 step, 2 step, 3 step. At this point, we can fire the first store operation because it meets its requirement. At this point, when we simulate for more steps, the circuit looks exactly the same as before. So now I simulate 1 step, but it looks exactly the same as before. So here we can say that the circuit reaches equilibrium. And from this point on, it will be always like this. So here we can already address our important intuitions for solving the problem. So apart from the FIFO, the components can always pass tokens ahead without stalling. And also forks can always trigger operations in an equivalent fashion. Now you might wonder, well, oh, that's cute, but how come it's going to be useful? And indeed, we can use this information to simplify the circuit. So let's go back to this frame before. Here we open up the logic behind it. We find out that the things are very expensive. But however, knowing the fact that the buffer can always pass tokens ahead without stalling, and also forks can always trigger the successor operation in equivalent fashion, you can remove the redundant logic out of it and only leave the simple part. So now not only they implement conceptually simple functionalities, they also have intuitively simple implementations. But however, here comes the important question. How can I guarantee that by doing these transformations, my circuit is still functional, right? Because let's recall that we are in a dynamic world. Everything can happen at any time. How can I make sure that circuit is still functional? So the idea is that, well, the problem is simple. We want to see if our design is correct. So you do functional verification. For instance, you generate stimuli to trigger the behavior of your circuit, and you inspect the traces that come out of it, and you see if it matches your requirement. But however, since we want a theoretical guarantee that our method is complete, this is not sufficient for two different reasons. First is that it is impractical to come up with all stimuli to cover all behavior of your circuit. Second, with limited amount of stimuli, it is impossible to be complete. So to solve this problem, we can leverage the power of formal verification, in particular by model checking, which refers to a mathematically rigorous way of checking that your model honors certain properties. And in particular, in all possible behaviors. And indeed, our goal is to have a formal verification framework for reducing the hardware complexity of HIS-produced data flow circuits. And the correct and also feasible formal verification requires an abstract verification model and useful formal properties that can spot the redundancies inside our circuits. Let's start from the formal properties. So let's go back to this example, which we are already familiar with. Then we can first introduce the first formal property, which is the equivalence of triggering. It refers to the phenomena that in different handshake channels, the movement of data tokens are always identical. So if the tool can show that this is true, we can merge the value signals of these components. Formally speaking, it means that the tool has to show that in all possible behaviors, the value signal of these handshake channels are always identical. So the next formal property is the absence of back pressure. Intuitively speaking, we can imagine that I were a data flow component. When I have a valid token to send, then this property means that my receiver is always ready to take it. So if the tool can show that this is true, we can set the ready signal that I see to a constant one because we know that it's constantly ready. And we can use constant propagation to simplify a lot of the logic inside our circuit. Formally speaking, the tool has to show that all possible behavior, the valid signal of the handshake channel always implies the ready signal of the same handshake channel. Let me give you an additional remark. So the transformation we have done to our circuit, it preserves sequential behavior. What does it mean? It means that our circuit has exactly the same performance, but with a much cheaper implementation cost. So as you can see from the example. Now we know everything about the formal properties, we can look into the formal modeling. So an additional remark, so the property we have described in the previous two slides, the only reason about token flow, or the only reason about the interactions between handshake signals. So as a consequence, it is a good idea to consider the modeling of your circuit to be independent of data. And in fact, for many of the data flow components, it is doable. For instance, irrespective of the value of the data token, the fork always duplicates data tokens, and the operators always synchronize the input data tokens to guarantee the functional correctness. And when we remove data from these components, the flow of token is still the same. We don't alternate how tokens flow. However, it is not the case for many other components. So for instance, in branches, the token steering actually depends on the control input. From the point of view of token flow, and in particular in this example, depending on the value of iterator and the loop bound, the flow of token behaves differently. For instance, the program might exit loop, or the program might repeat a new loop iteration. So since we want to reason about token flow, are we really gonna try out all possible values of the iterator token and also the loop bounds, it is simply impractical. It is the same as the simulation-based verification. So we can leverage a powerful idea, which is abstraction. So we introduce a new component, which is called a non-deterministic decider. So in place of the actual comparison, it provides arbitrary or randomized true or false control decisions. So without taking care of the actual values of the data tokens, we are able to model different control flow sequences. Let's not forget the fact that our circuit is connected to a memory. The memory is known for having so many different states for us potentially to consider. And furthermore, what makes it even more interesting is that in Dataflow circuit, we need to use a dynamic memory interface to handle out of order memory accesses from our circuit. So from the point of view of token flow, how can we reason about initialization interval, which means that how often my circuit can take data, or latency, how long does it take for me to retrieve a value from the memory? It is, so for consider these things, are we gonna try out to model all possible values of the configuration of my memory? And also, are we gonna really try out to consider all possible interactions between the addresses? It is also infeasible. So the idea is the same as before. We can leverage abstraction. So here we introduce a new component, which is called a non-deterministic wire. So which is essentially inserts random latency into the circuit, which provides arbitrary initialization interval and latency. So without explicitly modeling the state of the memory and the interactions between the addresses, we can model different memory access patterns and also the collisions. At this point, we can model arbitrary circuit that is generated from C or C++ code and do verification to spot the redundancy and also to do the simplification. However, scalability remains an issue, but luckily the non-deterministic construct we have described in these slides, they also improve scalability. In formal verification, it is very common to consider to break a very large model into smaller pieces and verify properties inside these pieces individually. So let's not forget the fact that our circuit is not just one basic block, it has many basic blocks. So we can partition our circuit and decouple our circuit into independent regions and verify properties in these regions separately. This is not enough. We also need to provide a tool that what's our assumption to the boundaries of these regions. One possibility is that we can model the boundary as random handshakes, so which never goes wrong. So far in this work, we have considered to decouple disjoint loop nests and also to decouple loops with different nesting levels. So now we are ready to evaluate our framework. So I'm going to walk you through the complete framework. So our method is based off of Dynamism, which is a standard, which is state-of-the-art HLS compiler for generating data flow circuits in RTL design. Rather than directly lowering everything into RTL, we redirect the intermediate structural representation to our newly developed model generator and property generator to generate a verification model and useful properties. We feed these things into a model checker. It returns a bunch of properties that turned out to be true, which represents the redundancy inside my system. And we can use this information to simplify our circuit accordingly. And we get a simpler RTL description. So now we are ready to evaluate the results. So the point of reference is non-optimized dynamically scheduled circuits produced by Dynamism. So our comparison is based on resource matrix, and we partition the benchmarks into two different groups. First, we have the regular workloads, and also we have the irregular workloads. So for the regular workloads, our method is very effective. It reduces 50% of the resource without a performance penalty. Because recall that our transformation did preserve sequential behavior, so the performance stays the same. So for irregular workload, this is where by applying dynamic HLS, you profit a lot, you gain a lot of performance. And indeed, most handshake logic are kept. They are proven to not be redundant, and they are essential for the dynamism. Let's not forget the fact that model checking the entire circuit does not scale. So, but remember that we proposed a compositional verification approach that can help us to improve the scalability to either So here is the result. We either make the missing bars appear in the end, or we massively reduce the checking time without penalizing, without hurting so much our capability of simplification. Then, so after applying so many different things, how far we are from static scheduling exactly? So here we change the point of reference to static scheduling, which are shown in the red lines. And we compare the matrix, we do the comparison with two different matrices, the resource matrix and also the execution time. So for regular workloads without resource optimization, here you can see that the dynamic design typically requires much more resource than static. By applying our method, we simplify quite a lot. There's still a gap between our best design, which are shown in the sky blue color, and the static scheduling. But we believe that since we only applied very simple properties, in the future, we'll be improving our result and make the gap smaller and smaller. But benchmark with irregular workloads, this is where our solution is Pareto optimal. And in particular, our solution Pareto dominates the dynamic design we had before. So now I would like to wrap up my presentation. So overall, our contribution is a form of verification framework for improving HLS-produced data flow circuits. We have a generalized data flow circuit model that captures all circuit behavior. Our set of properties are extensible. They spot the redundancy inside the circuit, and also we can use the information to reduce the cost of our circuit. To make our approach more practical, we propose compositional verification approach to ensure scalability. And overall, we make data flow circuits resource efficient without penalizing the performance. And I would like to thank you very much for your attention, and I'm open for questions.
Hi, really interesting stuff. So if I understood it correctly, you're like proposing questions to the model checker. Do you have an idea of what proportion that you're proposing valid questions? And if you could compute a tighter or more accurate program analysis, could you reduce the number of incorrect questions you're asking to the model checker?
Could you say it again? So it's a bit, so could you repeat the question?
Yeah, so if you improve the accuracy of your program analysis, could you only ask valid questions to the model checker that return true, rather than, if I understood correctly, you're asking lots of different questions and only a subset of those might be true?
Yes. I think I have a backup slide on this. Actually, I don't really have the accurate percentage of correctness, but I think it's actually a good point. So I guess it should be very low. So indeed, it should be very low, maybe below 20%. So above 20%, everything is kind of wasted checks. So to elaborate, it's like this.
Are you theoretically presented from like computing a really tight program analysis to tighten up those checks?
From practical point of view, I think we can use a different method. We can use simulation to filter some of the wasted checks. So rather than doing the analysis, we can just use simulation. So yeah, okay.
Thanks for the talk. Yeah, I have a follow-up question just on this. You actually you can generate conflicts, right? And you can add conflicts back to your properties. And when you do the formal checking, if you prune a large number of space, actually, if you search for conflicts, if you make a wrong proposal.
So you mean
do you do like conflict learning in the model checker?
So I guess you are referring to set solving, right? So
yeah, I mean the backbone are successful, right?
Yeah, so currently we are not using set solving. We are using BDD-based reachability analysis,
okay,
which is different, but we are exploring it. Yes,
I see. Okay,
that's set solving.
Yeah, just another question regarding these. Like, when you do this reachability test, like, do you actually have a bound? Do you have a certain bound of how much longer you're going to run? Is it bounded model checking or just like is a combinational actually in the formula?
Yeah, that's exactly the point. So when you do set solving based, you do bounded model checking. Right. But when you do BDD, you do complete model checking. So the only way to go is to put a timeout.
Oh, I see.
So,
So
yeah.
that's why you do partition. Otherwise, it
Yes,
doesn't
yes.
work. Okay, I see. Thank you.
Yeah, of course. That's cool. So, when you're trying to prove the absence of, say, back pressure
Mhm.
in your design, presumably there won't be absence of back pressure. I may design a situation in which a FIFO with a certain length, there isn't absence of back pressure, but I add another slot to the FIFO and now there is absence of back pressure. Is that something that you would pick up, or is it something that you could maybe look at as an optimization in the future?
Yeah, I would guess it's an optimization opportunity in the future. So for instance, let's go back to the simulation. So for instance, we can have different choices, right? So depending on how you describe the FIFO, so let's say it's a shift register, then let's say 3-stage shift register, then you completely eliminate all the back pressure in the system. Yeah, but it's additional detail, yes.
Thank you.